Okay, so welcome back, and now we're going to do case number 2. Case number 2 is very similar to case number 1, except what we're going to do is we're going to set it up for a comparison test with a series that is greater than the setup, greater than what we're defining our R value, or excuse me, a multiple of our R value. So we'll end up with another series, and then using the comparison test, we're going to show that that series diverges because this other series that we're going to relate it to also diverges. So this is going to be the case where rho is greater than 1. Okay, so case 2, we're going to assume again, case 2 is that rho is equal to this limit is greater than 1. So since rho is greater than 1, then we can say that there exists a real number r such that r is in between rho and 1, greater than 1, but less than rho. Okay, so now if we set it up that way, then we can let epsilon equal the difference between the two. So rho minus r, and that has to be positive, right, because of the inequality. So now we're setting up epsilon defined this way, which is greater than 0, and then of course we're going to use the definition of limits again. Okay, so what are we going to do? Okay, excuse me. So using the definition of the limit of a sequence, there has to exist an integer n, right? So using the definition of a limit of a sequence, or excuse me, of a series. Oops. There exists a positive integer n such that what? Well, what's the definition? The absolute value, right, of the nth term is less than epsilon, right? Or the difference between the nth term. So we're going to take the absolute value of a n plus 1 over a sub n minus what? Minus rho. That absolute value has to be less than epsilon for all n, right? For all n, oops, let me write it this way. So for all n greater than or equal to n, right? So that's just using the definition of the limit of a sequence. Okay, so now, therefore, now we can say this, right? So, therefore, what do we know? We know that, excuse me, okay, then R oh, I'm getting ahead of myself. I need to put. So therefore R equals epsilon minus, or excuse me, rho minus epsilon, right? Up here. So if we just do R minus epsilon, or rho minus epsilon. So if again, we're just using this equality here. And so we're going to say R equals rho minus epsilon, okay, is what? Is less than what? Okay, for all n greater than capital N. Okay, Now, to see that, we're taking this, which is rho minus epsilon, okay? And so if R, which is here, right? So R is less than epsilon, or excuse me, R is less than rho, then R, which is equal to this, is less than this, okay? For all n greater than or equal to some integer n. Okay, and so now we've got this. Now what we're going to do is we're going to set up the same kind of relationship that we saw before. So I'm going to erase this up here. So now, what does this give us? Well, this tells us that we can write R, right? So we can write the next term in the series as a multiple of the previous term of R, a multiple of R. So we can say that since this is true, then we can say that the absolute value of a sub n plus 1 let's do this, capital N, right, is greater than R times the absolute value of a sub n. Okay, so that's what we can say from the previous statement. And then, of course, if we start adding on, which this, so then what happens? Well, then we know that this must be true, right? A sub n plus 2 has to be greater than R times a sub n plus 1, right? But then with this, right, this is greater than this, which means that I can write this is greater than R squared times, oops, wrong. Greater than that. And then of course we can continue on and we can say, okay, then we could say n plus 3 is greater than R times the absolute value of a sub n plus 2. And then of course this is going to be greater than R squared times a sub n plus 1, which is going to be greater than R cubed times the absolute value of a sub n, and so on and so forth. Okay, now, then, since R is greater than 1, okay, right, what does this give us? This gives us a geometric series, right? We can use the geometric series. So the geometric series and the geometric series we're going to use is going to be what? It's going to be R times the absolute value of R sub n plus R squared, times the absolute value of a sub n plus R cubed times the absolute value of a sub n, and so on. Okay, so now, this geometric series diverges. Okay, we know that. Why? Because r is greater than 1. So we can use this geometric series that diverges. Now, then we can use the comparison test because we know that what? This series, or the fact that this is an increasing, right? This is increasing sequence. And what? This is a divergent series. And so by the comparison test, since we know that this diverges, then the other sequence diverges. So we can apply the convergence test and we can conclude that what? Diverges. And so then therefore, since this diverges, okay, therefore the series diverges. And we're done. Now, for part 3, we're going to show that the test does not provide any information if rho equals 1, and we're going to consider the p-series. Okay, so in the last case, which I'm not going to do a separate video for because it's a short proof, is in case 3, where rho equals 1, what we're going to do is we're going to consider the p-series, okay, and show that this is inconclusive. Okay, doesn't provide any information if rho is equal to 1. So the p-series 1 over n to the p, right? So we're going to consider let's consider the p-series for any real number p. Okay. And so we're going to say that the rho equals 1. Okay, so we're going to use, again, the ratio test, so the limit as n approaches infinity of 1 over n plus 1 to the p over 1 over n to the p equals, then we're going to just simplify this. And when we simplify this, this is just going to jump on top. And so we get a limit as n approaches infinity of n to the p over n plus 1 to the p. And then what we can do is we can Set that equal to 1. Okay. Now, however, we know what? We know that a p-series diverges if p is less than or equal to 1. Whereas the p-series converges if p is greater than 1. Okay? Oops. Oh, wait a minute. Okay, so it's inconclusive when this thing is going to diverge and converge using the ratio test if this is equal to 1. Okay, that's it. Have a great day.